Hello, I'm Brett Sheeran and I will be discussing the introduction portion of the column buckling experiment. The experimental objectives of this experiment included determining the behavior of a column under a compressive load, determining how flexural stability is affected by column length and fixity, and observing the effects of imperfect load alignment on experimental results. One key point I would like to establish is that a column is a structural member that is designed to carry compressive axial loads. So, we apply column buckling theory in order to obtain calculated results so that we can compare them to our experimental results. It is found through a set of governing equations and assumptions that the critical load is equal to pi squared EI over L squared, where EI represents the flexural stiffness of the column and L represents the length of the column. We will see that an imperfectly loaded column will begin buckling before the predicted value of critical load, and we should see an asymptotically increasing load as the deflection goes to infinity. We started with the governing equation of transverse load and made assumptions in order to come up with equation 2. We assume no distributed axial load, no axial rotation was negligible, and so were nonlinear quadratic terms. In equation 2, n represented a compressive load such that the negative n was equal to compressive load, shown down here, and W represents the deflection. Equation 2 was then plugged into the governing differential equation for transverse load, and equation 3 was established. The solution to this equation is depicted in equation 4. Constant coefficients are labeled with a C, and K equals the square root of P over EI. Using column buckling theory, these were our predicted values. So you can notice, as the length of the column increases, the critical load for both the pinned and clamp conditions decreases. So we should notice this in our experimental results. Experimental results should yield graphs similar to the ones shown in figure 1. The load should approach the calculated critical load at which the columns buckle. The point at which the load becomes asymptotic will decrease with imperfections as well.
Hi, I'm Ryan Gleckner, and I'm going to be going over the background of this experiment. So, as an overview, the lab was completed in room 42 of the Hammond building. We used a column buckling apparatus to ensure that the load was applied purely axially, because if you have any other forces in there, if you have a moment on there, it's going to cause the column to buckle prematurely, which will have our data show that the critical load is much lower than it actually is in reality. A linear variable differential transformer was used to measure the displacement at the midsection of each column where the buckling would be most extreme. And a S-beam load cell was used to measure the force applied to the column. And the load on the column is approximately 3 times the load measured by the load cell, because we had to balance out the equations and the moment balance to get the transition from the load cell load onto the column. You can see our setup here. There's the load cell right here, the column over here, the linear variable differential transformer, which is measuring our displacement again. You can see here it's right in the middle of the column. Here we have the method of clamping or stabilizing the column as we tested it. It's currently in the pinned setup for this picture, but it can also be put into a clamp setup where the ends are not allowed to rotate at the boundary condition. This beam here has a level on it to again ensure that the load applied to the column is purely axial and there are no moments being applied, which would again cause it to have a bending moment and buckle too early. So here you can see what would happen if during buckling with a pinned boundary condition. The ends actually rotate and the column buckles sooner. Here you can see with the fixed clamped boundary condition where the end of the column actually stays perpendicular to the wall. We tested 3 separate columns of lengths 18 inches, 21 inches, and 24 inches. You can see them all here. They are made of aluminum.
Hello, I'm Patrick Julick, and I'll be covering the results of this experiment. So here we have the results for the pin boundary condition, and this is using the asymptotic method. So on the x-axis we have the load, and then on the y-axis we have deflection. And as the load reaches the critical load, it asymptotically goes to infinity. So for the 24-inch beam, the asymptote is around 50 pounds, and for the 21, it's around 65 pounds, and then for the 18-inch, it's around 70 pounds. And then to get more precise numbers, we use a data transform to get the imperfection method, and the slope of these lines is equal to P critical, and the only change is the x-axis is now displacement over load instead of just load. And this gives us slopes of, for the 18-inch pin condition, 72 pounds, for the 21-inch, 67.2 pounds, and for the 24-inch, 57.7 pounds. So they are slightly higher than the estimations we made for the asymptotes, because this is a better approximation of that. So here we have the results for the clamp section. For the 24-inch, it looks like it's about 170 pounds. And then for the 21-inch, it looks to be going at 200 pounds. And then for the 18-inch, we didn't get enough data close to the asymptote to get a great estimation, but it looks like it's asymptoting around 270 pounds. And then using the imperfection method again, we found that the 24-inch clamped beam had a critical load of 155 pounds. The 21-inch clamped beam had a critical load of 218 pounds, and the 18-inch clamped beam had 284 pounds. All of these values are much lower than the theoretical values, and that could be due to a number of errors that will be covered in the next section.
Hi, I'm Jonathan Rogers, and today I'll be discussing the results, the errors, and the conclusion that we determined in this experiment. So number 1, the percent error. We determined from our P critical values and using the formula pi squared EI over L squared, and for the asymptote, the pin method, and then for clamps we use 4 times pi squared EI over L squared. We determined those values, and using the asymptotic method determined from our data, and the imperfection method, which was the deflection over load, as discussed in the previous graphs, we determined our percent errors. Now, our highest percent errors for our pin values, utilizing the asymptotic method, was 37%. That was in the 18-inch pin, and our highest percent error for our pin for the imperfection method was a 35%, also for the 18-inch pin. For the clamped values asymptotic method, our highest percent error was 21%, or 21-inch clamps, and additionally the 155 load for the imperfection method was about a 38% error. To explain some of the high percentage errors that we had in the previous slide, the number one issue that we think that could have affected our data points would have been the initial column displacement, meaning that over the years and the multiple experiments that have been done from different sections, we think that the columns may have fatigued or deformed in a plastic deformation type way that would have affected our data or caused the column to deflect in one way or another a little more easy and guide the data so that the data points may have been affected in a wrong manner per se. That would have been the main concern regarding our data points and why our values would have been, the percent error values would have been so high. The second reason would have been movement from the clamps. So the clamps were hand tightened and of course might have shifted a little, allowed some movement within the little notch for both the clamped and the pinned. That may have allowed the metal to not be seated perfectly, and it would have affected the perfect pinned or perfect clamped values that we. The last thing that would would have accounted for our error would have been the manual level adjustments. This has more to do with the apparatus, such that there were two handheld tightening mechanisms that allow us to apply the load to the column. Arranging the apparatus such that there was only one gear that needs to be tightened would simplify the process greatly and improve the accuracy such that the level would have been easier to determine whether or not it was flat and perpendicular to the column. Last thing would have been the load may have not been perpendicular given that we did have two gears, and that would have accounted for some of the error such that it would have allowed the force to perfectly align through the neutral axis and not at an angle, had it been flat and not imperfectly level. In conclusion, the purpose of this experiment was to investigate and determine the behavior of a column under compressive load using experimental results and beam bending theory. Second, to determine the flexural instability and how it's affected by column length and fixity. Observe the effects of imperfect load alignment and column straightness on the experiment results versus the predicted results. We accomplished this objective and determined that a clamp support system utilizing a shorter column length is the most ideal system for any type of aircraft wing or building architecture or engineering in general. This result makes sense because if both ends of the column are clamped, there cannot be any moment at these points, which effectively makes the column shorter. Additionally, you can also improve, we talked a little about this in the air, but you can improve this experiment utilizing an apparatus that accounts for or has self-leveling capabilities. This, of course, makes our error smaller, or would theoretically make our data points more accurate towards our theoretical critical load. Additionally, you can also use non-fatigue columns. That would be the main point of making our data points that much more accurate. This concludes the briefing.